Hello students, welcome to this video on System of Particles and Rotational Motion part 5, which is given in chapter number 7 of Physics for class 11. We have seen in previous chapter the analogy between rotational motion and translational motion. For example, the angular velocity omega plays the same role in rotation as the linear velocity v in translation. In this section, we wish to take the analogy further. In doing so, we shall restrict the discussion only to rotation about a fixed axis. So, this video covers section 7.11 Kinematics of Rotational Motion, Section 7.12 Dynamics of Rotational Motion, Section 7.13 Angular Momentum in Rotation, and Section 7.14 Rolling Motion. The study of this section needs a thorough study of our videos and discussions in part 1, 2, 3, and 4 of chapter number 7. Please go through the previous sections. The links for the same are given in the description part of this video. I welcome you once again. Please note down all the important points, or the same will help you in answering complicated problems. Kinematics of rotational motion or rigid body rotation. Consider the angular displacement of rotating body where we take any particle like P of the body. In the diagram on the right hand side, the point P lies on the rotational path and it lies within the body. Its angular displacement theta in that plane it moves is angular displacement of the whole body. P is moving in a circular path with center at C. The origin of this coordinate is O and the axes are X, Y and Z. This is the origin, whereas the point P can move in any of its plane of rotation. So this plane of rotation is marked in the dotted lines. So theta is measured from the fixed direction in the plane of motion of P, which we take it to be x dash axis chosen parallel to the x axis. You see here x dash, the plane x dash is parallel to x axis, y dash is parallel to y axis, and z is coincides with the z axis. And the plane of motion of the particle is xy plane. This particle P is moving in xy plane. Theta naught is the angular displacement at t equal to 0. Here the first red line, it makes an angle theta naught, and at the time t equal to 0. Let us proceed to derive the equations of motion. Equation of rotational motion. We know that the angular velocity omega is the time rate of change of angular displacement. That is, by definition, omega is equal to d theta by dt. Here, because the angular velocity is about the rotation in the fixed axis, that is, the axis of rotation is fixed, we may or we may not represent angular velocity as a vector. The angular acceleration is given by alpha is equal to d omega by dt. Therefore, the kinematical quantities in rotational motion that is angular displacement theta, angular velocity omega, and angular acceleration alpha respectively are analogous to kinematic quantities in linear motion. We have seen in earlier videos the linear velocity, linear displacement, and linear acceleration were represented by x, v, and acceleration as vector a. We know the kinematical equations of linear motion with uniform acceleration is given by x is equal to x naught plus v naught t plus at square. These are all our basic equations of linear motion. So there are three equations. Second equation is v is equal to v naught plus half at. Here x naught is the initial displacement, v naught is the initial velocity, and a is the acceleration, and t is the time. The third equation is v square is equal to v naught square plus 2ax. Let it be equation 1, 2, and 3 respectively as shown on your screen. Here x naught is the initial displacement and v naught, as I said, v naught is the initial velocity. The word initial refers to the values of the quantities at time t is equal to 0. The corresponding equations for rotational motion with uniform angular acceleration are omega is equal to omega naught plus alpha t, theta is equal to theta naught plus omega naught t plus half alpha t square, and omega square is equal to omega naught square plus 2 alpha into theta minus theta naught. Let these be equation 4, 5 and 6. Here, as said earlier, theta naught equals initial angular displacement of rotating body, and omega naught equals initial angular velocity of the body. Derive the three equations for rotational motion under constant acceleration. That is, first equation omega is equal to alpha t plus omega naught. The second equation of rotational motion, theta is equal to omega naught t plus half of alpha t square, plus the third equation omega square is equal to omega naught square plus 2 alpha theta from the first principle. Let us answer. Angular velocity omega is equal to d theta by dt by definition. Therefore, since it is given that angular acceleration is uniform or constant, therefore d omega by dt is equal to alpha, that is acceleration, angular acceleration is equal to constant. Therefore, integrating the above equation, we get omega is equal to alpha into dt, that is omega is equal to integral alpha into dt, that is equal to integral alpha dt plus c, that is this c is constant of integration. Therefore, omega will be equal to alpha. Alpha is constant taken outside. Integral of dt is t plus c, as alpha is constant. Therefore, at the time t equal to 0, omega is equal to omega naught. Therefore, this above equation becomes omega is equal to alpha t plus omega t. Let it be equation 1. Now we will derive the second equation. We know that omega into dt is equal to d theta. Now we will put the value of omega from equation 1. That is, omega is equal to alpha t plus omega naught. Therefore, this above step becomes omega naught plus alpha t into dt, that is equal to d theta. Now we integrate the above step both sides. We get integral 0 to t of omega naught plus alpha t into dt is equal to integral 0 to theta d theta. That is, at the time t, the angular displacement is theta. Therefore, the limits are 0 to t and in the time scale and 0 to theta in the displacement. Therefore, integrating, we get omega naught t, that is omega naught dt is omega naught t plus integral of alpha t will be, alpha is constant, t dt will be t square by 2 and the limit is 0 to t, that is equal to theta on the right hand side, 0 to theta, upper limit is theta here. Putting the upper and lower limits and simplifying, we get omega naught t plus half of alpha t square, that is equal to theta. Therefore, this equation can be rearranged as theta is equal to omega naught t plus half of alpha t square. Let it be equation 2. Now we will proceed to derive the third equation of rotational motion. Evaluating for t from equation 1, we get t is equal to omega minus omega naught over alpha. Substituting or putting the value of t equals omega minus omega naught t over alpha in this equation 2, we get theta is equal to omega naught into omega minus omega naught over alpha plus half of alpha into omega minus omega naught over alpha whole square. You please write down these steps slowly and slowly. And rearranging, we get omega square minus omega naught square is equal to 2 alpha theta, or omega is equal to omega square plus 2 alpha theta. Let it be equation 3. Hence, we have derived all the 3 equations for rotational motion. Dynamics of rotational motion about a fixed axis. Table shown on the screen gives a comparative statement of linear and rotational motions. We use terms displacement, velocity, acceleration in linear motion. Displacement is represented by x, velocity v is equal to dx by dt, and acceleration is a is equal to dy by dt. The analog of these three terms in rotational motion are angular displacement theta. Theta, it may be in degrees. Angular velocity is represented by omega, that is equal to rate of change of angle, that is angular displacement d theta by dt. Similarly, acceleration a is equal to dv by dt, and angular acceleration is represented by the symbol alpha is equal to d omega by dt. The moment of inertia is analog of mass, which is used in linear motion. So, moment of inertia is in rotational motion. Force is represented by ma, and correspondingly the analog of force is torque. Tau is equal to I into alpha, where I is the moment of inertia. Work done is dw is equal to f dot ds, and work in rotational motion is related as w is equal to tau d theta. The kinetic energy in the case of linear motion is k is equal to mv square by 2, and in rotational motion it is k is equal to I omega square by 2. The power P is given by F into V, that is force into velocity. Whereas power in rotational motion is related as P is equal to tau omega, where tau is the torque and omega is the angular velocity. Linear momentum in linear motion is P is equal to small p is equal to mass into velocity, whereas angular momentum L, capital L, equals moment of inertia capital I into omega. We also have three linear equations which we are using very frequently in physics, that is in linear motion. Correspondingly, the rotational motion also has three equations when alpha is equal to 0, that is the acceleration equal to constant, acceleration equal to 0 or constant. Therefore, when acceleration is constant or uniform acceleration, omega is equal to omega naught plus alpha t, and theta is equal to theta naught plus omega naught t plus alpha t square, and omega square is equal to omega naught square plus 2ax. These are similar to all the linear motion equations of motion in linear motions. In the case of linear motion, when alpha is not a constant, we have to take the differentials. So omega by definition is equal to d theta by dt, and alpha is equal to d of omega by dt or d square theta by dt. And we also have omega d omega is equal to alpha d theta. Next we have a table giving the details of symbols, dimensions, units and remarks of angular or rotational motion. Angular velocity is represented by vector omega, and dimensions are t to the power of -1, and its unit is radians per second. We have a relationship velocity with linear velocity vector v is equal to vector omega into vector cross omega r. So v is equal to omega cross r, that is the dot product or a vector product. Angular momentum is represented by capital L, and its dimensions are ml square t to the power of -1, and its unit is joules second. And the relationship of L, angular momentum with angular velocity and momentum, is given by capital L. Linear momentum is capital L is equal to omega cross small p. Small p is the linear momentum. Torque is represented by a Greek letter tau, and it's a vector, and its dimensions are ml square t to the power of -2, and its unit is Newton meters. And its relationship with linear motion is tau is equal to r cross F, where F is the force. Moment of inertia is represented by the symbol I. I is a tensor quantity. It is neither a scalar nor a vector. It is a tensor quantity. Its dimensions are ml square, and its unit is kg meter square. And I, moment of inertia, I is the summation of 1 to I equals 1 to summation of each particle 1 to n of mi or I square. I is equal to 1 to n. Dynamics of rotation about a fixed axis. Let us solve some numerical problems. The angular speed of a motor wheel is increased from 1200 rpm to 3120 rpm in 60 seconds. Question part 1. What is its angular acceleration, assuming the acceleration to be uniform? And part 2, it is how many revolutions does the engine make during this time? Answer. Please analyze the problem and read the question once again. We will answer it. Here the angular speed is changed, that is omega naught minus omega. Omega naught is 1200 and omega is 3120 and t is 16 seconds. So we have to find the angular acceleration. Please recall the relationship equation. Omega is equal to alpha t plus omega naught. So where omega naught is the initial angular speed in radians per second. Therefore, omega naught is equal to 2 pi into angular speed in revolutions per second. Please note here we are required to convert radians per second to revolutions per second. Therefore, converting, we get 2 into pi into angular speed in revolutions per minute divided by 60 seconds per minute. Therefore, that is equal to 2 pi into angular speed. Initial is 1200 rpm. That is rpm here. Revolutions per minute divided by 60 radians per second. Therefore, that is the omega naught is equal to 40 pi radians per second. Please go and calculate it very meticulously, step by step. Final angular speed in radians per second omega is equal to 2 pi into 3120 divided by 60. Using this relation, we again convert the given speed 3120 into radians per second. Therefore, that is 2 pi into 3120 divided by 60 per second. Therefore, simplifying, we get 2 pi into 52 radians per second. That is equal to 104 radians per second. The angular acceleration alpha is given by the relationship alpha is equal to omega minus omega naught divided by t. This is, we are rearranging the terms of this equation. So we get omega minus omega naught divided by t is equal to, substituting the values of omega and omega naught, and t is taking t as 16 seconds, we get the answer as 4 pi radians per second square. So angular displacement, we are also required to calculate angular displacement is equal to theta is equal to omega naught t plus half alpha t square. Substituting the values, we get omega naught is 40 pi, we have calculated here, into 16, t is 16 seconds, plus half into 4 pi, that is alpha is 4 pi. We have calculated here acceleration as 4 pi into 16 square. That simplifying, we get 1152 into pi radians. So therefore, number of revolutions will be equal to 1152 pi divided by 2 pi. That is equal to pi gets cancelled. That is 1152 divided by 2 is equal to 576. So to convert radians into number of revolutions, we have to divide it by 2 pi. Next question. Obtain an expression for the work done by a torque. Hence, write the expression for power. Consider a rigid body rotating about a fixed axis as shown in figure. This is the figure shown here. This is a This is axis is at O and the body is rotating about a fixed axis at O point. At point P on the body is rotating about an axis perpendicular to the page. So axis is perpendicular to this screen. This is perpendicular to the point O here, which is going directly into the screen. A tangential force F is applied on the body. It produces a small displacement ds on the body. So tangent force capital L shown in the red arrow is applied. The work done dW by this force is dW is equal to F dot ds. But ds is equal to r d theta. That is from the geometry of the figure. So ds is equal to r d theta. Therefore, dW is equal to F dot r into d theta. But F dot r is tau. We know from the definition of torque, F dot r is tau. Therefore, dW is equal to tau d theta. This expression gives the work done by the external torque tau, which acts on the body rotating about a fixed axis through an angle theta. Instantaneous power, we will also calculate the power because it is asked in the question. Instantaneous power is equal to P, capital P is equal to dW by dt. Substituting dW is equal to tau d theta, that is from equation 1, we get P is equal to tau into d theta by dt. Hence P is equal to tau into omega. Because angular velocity d theta by dt is omega. We have studied about angular displacement, angular velocity, angular acceleration, and angular momentum in section 7.7 of our video. The link for the same is given in the description part of this video. Let us quickly review what we have learned. The linear momentum of a body with respect to any axis of rotation is known as the angular momentum. This is the by definition. Therefore, if small p, vector p is linear momentum of the particle and r, vector r is its position vector from the point of rotation, then angular momentum represented by symbol capital L, vector L equals vector r cross vector p. That is the cross product or vector product of position vector and point of and momentum. This cross product results in a vector L which is perpendicular to the plane of position vector and linear momentum. So it can be represented also as L is equal to R modulus of P sin phi n unit vector n. So here R is the position vector, P is the linear momentum, phi is the angle between R and P. The vector L is perpendicular to the plane of R and P and hence it is represented as n unit vector n, which is perpendicular or normal. In vector form, L can be written as capital L is equal to I omega, where I is the moment of inertia and omega is the angular velocity. From this relationship, L is equal to I omega, we can write by differentiating dL by dt is equal to I into d omega by dt. Or we can write also as d omega by dt as alpha. Alpha is the acceleration. Therefore, dL by dt is equal to I alpha. That is nothing but the torque, tau vector r. So this is equivalent of rotational analog of Newton's second law of motion. If a large torque acts on a particle for a small time, then angular impulse represented by symbol vector j of torque is given by j is equal to integral tau dt, that is equal to tau average of integral t1 to t2 of dt. Therefore, angular impulse j is equal to change in angular momentum. Law of conservation of momentum. So, if the net external torque on a particle of a system is 0, that is dl by dt equals tau equals 0, which we had derived previously equals 0, then the law of conservation states that capital L, that is the angular momentum, equals sum of all the angular momentums, that is capital L is equal to L1 plus L2 plus etc up to Ln, that is equal to constant. So if the torque is 0, then angular momentum is constant. This is the law of conservation of momentum. We know that L is equal to I omega. So if tau is equal to 0, then I omega is equal to constant. This is also a law of conservation. It is represented, this relationship represents law of conservation of momentum. Angular momentum of a system, may be of a particle or a body, remains constant if resultant torque acting on it is 0. In section 7.14, we will discuss about rolling motion. Before we discuss in detail about rolling motion, we will just recapitulate what is slipping, spinning and rolling, which we have studied in section 7.1 of our video, whose link is also given in the description part. Slipping. When the body slides on a surface without rotation, please note without rotation, then its motion is called slipping motion. In this condition, the friction F between the body and the surface is 0. Therefore, body possesses only translatory kinetic energy K suffix T is equal to half mv square. This translation is shown here above in the figure, first figure. Number 2, spinning. When a body rotates in such a manner that its axis of rotation does not move, then its motion is called spinning motion. In this condition, the axis of rotation of a body is fixed. In spinning, the body possesses only rotary kinetic energy K subscripts R equal to half into I omega square. Here please note, in spinning the axis of rotation does not move. Please underline it. Next part 3. Rolling. If in case of rotational motion of a body about a fixed axis, when the axis of rotation also moves along with the body, then motion is called combined translatory and rotary motion. That means in rolling motion, there is axis of rotation also moves and the body also moves. Both move. For example, motion of a wheel of a cycle on the road. When a cycle moves, the axis of rotation of the wheel moves as well as the cycle itself moves. Similarly, motion of a football rolling on the surface. In this condition, the friction of the body and surface is not equal to 0 because some part of the body is always in contact with the surface. Body possesses both translational and rotational kinetic energy. Net kinetic energy equals translatory plus rotary kinetic energy. In case of combined translatory and rotary motion, if the object rolls across the surface in such a way that there is no relative motion of the object and the surface at the point of contact, the motion is called rolling without slipping. In this section, we are considering rolling without slipping. Kinetic energy of rolling motion. Please see the figure here. Here, in the case of rolling motion, the friction between, this is the surface, the friction between the body and the surface, this is the dotted lines or cross lines are surface, and this is the body, rolling body. So F is not, friction is not equal to 0. The body possesses both translational and rotational kinetic energy. Therefore, net kinetic energy is equal to translatory plus rotary kinetic energy. The kinetic energy of the system of particles is given by is equal to kinetic energy of the translational motion of a center of the mass. This is the center of the mass, and its kinetic energy is given by half mv square plus kinetic energy of the rotational motion. That is, as the body starts moving, there is a kinetic energy, and it is represented by kinetic energy due to motion as k dash. Therefore, the total net kinetic energy capital K is equal to capital K dash plus half into mv square, where m is the mass and v is the velocity. The velocity vectors, linear velocity is shown here. The linear velocities of the body rolling on the surface is shown here. This equation can also be written as the kinetic energy of a rolling body, therefore is given by K dash is, we know, half of I omega square. Therefore, K is equal to half of I omega square plus half m mass into V cm. This is velocity at the center of the mass, because different particles will be moving with the different velocities, but we have to consider here velocity of the center of the mass. The kinetic energy is given by K is equal to half of I omega square plus half of m v cm square, where m is the mass of the body and v cm is the center of the mass velocity. Since the motion of the rolling body about the center of mass is rotation, K dash represents the kinetic energy of the rotation of the body, where I is the moment of inertia about the appropriate axis, which is the symmetry axis of the rolling body. Now we substituting, we have proved in the previous equation I is equal to mk square. Here k is the radius of gyration. We have also studied about radius of gyration in section 7.9. So that is also, the link for this is given in the description part. Please click and revise that. Therefore, substituting I is equal to mk square, where k is equal to corresponding radius of gyration of the body and vcm is equal to r omega, where r is the radius and omega is the angular velocity. We get k is equal to half into mk square. Capital K is equal to half of m small k square into VCM by R whole square plus half M VCM square. Therefore, capital K is equal to half of M VCM square into 1 plus K square R square. Please note this small k is the radius of gyration. For clarification, I have given it in it is given in black color. Capital K is the kinetic energy. Therefore, friction is responsible for this type of motion, but work done or dissipation of energy against friction is zero, as there is no relative motion between the body and surface at the point of contact. Rolling motion of a body may be treated as a pure rotation about an axis through point of contact with same angular velocity omega. So the relationship between linear velocity and angular velocity is V is equal to R omega, where R is the radius. In case of rolling, all points of the rigid body have the same angular speed. Rolling on an inclined plane. Please refer to the figure on the right hand side. In the figure, an object kept at the point B, initially at rest, moves down the inclined plane. This is the inclined plane. S is the inclined plane. Say this end is A. AB is an inclined plane whose length is S, and B is at a height of H from the point C as shown in the figure. The angle between AB and BC and AC is theta. So the body undergoes both rotation as well as translation. So let us discuss in detail. When a body of mass m and radius r, capital R, rolls down an inclined plane of height h and angle of inclination theta, it loses potential energy. However, it acquires both linear and angular speeds, and hence the total gain of kinetic energy is due to translation and that of rotation. In the case of rolling motion, potential energy lost is equal to potential energy gained. Therefore, equating both potential energy and kinetic energy, we can write the equation as mgh is equal to half mv square into 1 plus k square by r square. This we have derived in the previous section. Or we can write simplifying, cancel m and m on both sides, on the left hand side and right side, and evaluate for v. We get v square is equal to 2gh divided by 1 plus k square by r square. Here v is the linear velocity, g is the gravitational constant, acceleration due to gravitation, h is the height, and small k is the radius of gyration of the body, and r is the radius or distance. And velocity can be expressed as at the lowest point, that is at the point A. A is not written here, but you can, while copying, you can write it as A. The lowest point V is equal to square root of 2gh divided by 1 plus k square by r square. And acceleration can be obtained by writing from the equation v square is equal to u square plus 2as. We are already familiar with this relationship. Therefore, A is equal to, we have to substitute in this equation u is equal to 0 because the body is at rest initially, and S is equal to h divided by sin theta, that is from the geometry of this triangle, and V is equal to square root of 2gh divided by 1 plus k square by r square. Therefore, we get the value of A as A is equal to G sin theta divided by 1 plus K square by R square. And we can also obtain the equation for time from the equation V is equal to U plus AT, or T is equal to, by substituting U is equal to 0 and value of V and A from the above expressions, we can write it as T is equal to 1 over sin theta square root of 2h by g into 1 plus k square by r square. This you please obtain by writing the values of V and A from the previous equations. Now we will take up some short questions of 3 marks. Prove that the rate of change of angular momentum of a system of particles about reference point is equal to the net torque acting on the system. This was the question asked in the previous year's examination of 3 marks. This we have already given in section 7.7.2 and 7.7.3. Please click the link given in the description part of this video. Question 5. 3 mass point M1, M2 and M3 are located at the vertices of the equilateral triangle of side A. What is the moment of inertia about an axis along the altitude of triangle passing through M1? So the figure is shown here. A, B and C are 3 vertices and masses and 3 mass points of M1 at A, M2 at B and M3 at C. This is an equilateral triangle. Each side is A, as shown in the figure. So, if you take the draw perpendicular from A to BC, we get BD is equal to A by 2 and DC is equal to A by 2. Therefore, I is equal to, we know that sigma I is equal to 1 to n of Mi into Ri, where m is the mass and r is the distance. Therefore, I is equal to m1 into 0. Suppose we take the point 1, 0 square plus m2 into BD, that is the vertical distance from this axis. So, m2 is equal to A by 2 BD plus m3 into DC. So, substituting BD and DC as A by 2, we get I is equal to A square by 4 into m2 plus m3, where A is the distance of each side of the length of each side of the equilateral triangle. Next question, question number 6. A disk rotating about its axis with angular speed omega is placed lightly without any linear push on a perfectly frictionless table. The radius of disk is capital R. What are the linear velocities of the point A and B and C on the disk shown in the figure? Will the disk roll? Please see the figure here. And A is the top point and B is the point touching the surface, a frictionless surface, and it is rotating in anticlockwise direction omega naught as shown in the figure. And the distance between R and B is center, and point B is a capital R, and point C, center of mass, and the center of the circle is R by 2. It is shown in the figure. Therefore, for A, at point A, VA is equal to R into omega naught in the forward direction. VB is equal to R into omega naught in the backward direction. It is the direction at point, it will be in the backward direction. And at point C, VC is equal to R by 2 into omega naught. So at any point inside C, distance is R by 2. Therefore, for C, it is VC, velocity at C is equal to R by 2 into omega naught in the forward direction. Disk will not roll because forward and backward direction. rotation in forward and backward direction. Next question. Three bodies, a ring, a solid cylinder, and a solid sphere roll down the same inclined plane without slipping. They start from rest. The radii of the bodies are identical. Which of the bodies reach the ground with maximum velocity? In the case of rolling motion, the potential energy lost is equal to kinetic energy gained. Therefore, mgh is equal to half mv square into 1 plus k square by r square, where k is the radius of gyration, v is the velocity, h is the height. So, v square is equal to 2gh divided by 1 plus k square by r square. We have proved it in the previous slide. Therefore, we will take each case of ring, cylinder and solid sphere. So, in the first case, k square is equal to r square. Therefore, here if we put k square is equal to r square, v square will be is equal to, v will be equal to square root of 2gh. This k square equals r square formula we have given in the our table in this previous video. So for solid cylinder, k square is equal to r square by 2, that is equal to, therefore v is equal to square root of 4 by 3 gh. That is, if you put k square is equal to r square by 2, r square gets cancelled, therefore it becomes 4 by 3 gh, that is v is equal to square root of 4 by 3 gh. Similarly, if for a sphere, we have to please go through the table in the previous video wherein we have given the radius of gyration for a sphere as k square is equal to 2r square by 5. Substituting the value of k square as 2 square by r square in this equation, we get v is equal to square root of 10 by 5 gh. Please note down and work out yourself step by step. Next question. Find the torque of force 7I minus 3J minus 5K about the origin which acts on the particle whose position vector is I plus J minus K. This is question number 8. Similar problem we have solved earlier. Let us repeat it. We know that tau torque is equal to R cross F, where tau is the torque, R is the position vector and F is the force. So R is given as I plus J minus K and force is given, F is given as 7I minus 3J minus 5K. Therefore, we can find the cross product of R and F by writing the using matrices. Therefore, tau is given by equals matrix ijk in the first row and coefficients of R in second row, that is 1, 1 and minus 1, that is I plus j and minus 1. The ratio is coefficient is 1 here and plus 1 here and minus 1 here in this R, and coefficient of F are 7, minus 3 and minus 5. The same thing we have repeated in this matrix. Therefore, simplifying the matrix and using the knowledge of matrix algebra, we get minus 8i minus 2j minus 10k. This we come to the conclusion of chapter number 7. Next lecture we will take up chapter 8 on gravitation. Till then, goodbye.